Hello everyone, my name is Fatemeh Hossein Nouri from Center of Theoretical Physics in Warsaw. I would like to thank the organizers for giving me this opportunity to present the results of our research project. So this is the title. We basically investigate the gas environment effects on gravitational waves from the high mass residual binary black holes. So let me start with an introduction. So we know that supermassive binary black holes emit low frequency gravitational waves, and there's a possibility that we can detect them with the future laser interferometer such as LISA. And we know that such binary systems are usually inside the accretion disk at the center of AGNs. We already know several candidates of such systems. And if you look at the literature, you basically found a series of studies that they somehow adapt what they call it like the planet migration in planetary accretion disk. They adopt the same kind of analysis for the binary black holes in the accretion disk, and they suggest that this gas environment can impose some extra torque. And this torque will actually impose some measurable imprints in the gravitational wave signal, which can be detectable by LISA in the future. And so there are basically even more papers like that. But all this works actually assume a very simple approach for the accretion disk. They use just a simple alpha disk model. But we know that the alpha disk models are hypothetical objects, and the alpha viscosity is really an artificial viscosity. So in real world, we kind of expect that if we have magnetic field inside the accretion disk, this differential rotation inside the accretion disk should trigger the magnetorotational instability, and this instability is responsible for the angular momentum transport in the accretion disk. And so we basically, in this study, we wanted to do this realistic scenario. So we have the thin accretion disk, and we evolve it with the magnetic field. And then from that, we quantify the alpha viscosity, and we estimate the gas torque from it. So we come up with a very simple approach. So first of all, the secondary black hole is not included in our simulation. So we only evolve the magnetized accretion disk to see that how much turbulence we can get from this model and how much torque can be created by this. So for our numerical simulation, we use our developed version of the HARM-COOL. And so we are evolving the disk in a two-dimensional grid with this resolution, and we evolve up to like 60,000 co-units. And so for the initial configuration, we use this thin disk structure from the India's paper, and which is actually creating some disk like this. And we basically scale our results for a case of the primary black hole of 10 to the 6 solar mass and the mass ratio of 10⁻³ . And okay, so we have this non-zero component of the vector potential for initial magnetic field, and this M parameter is basically a parameter which controls the inclination angle of the initial magnetic field. So here we see the differences. So higher M basically means higher inclination angle for the colloidal field, and this is like lower M equals 0.1. So we basically evolved several cases. In each case, we alter different things like magnetic strength and also the inclination angle and also black hole spin. Since this beta parameter is a bit misleading, perhaps we've got like a very high magnitude here, but it's not like that. So as a comparison, I'm showing the maximum of the beta on the equator as well. So here in this plot, you can also see that overall we have like two cases of initially low magnetized and two cases of initially high magnetized. We have this comparison. Okay, now let's evolve the system. Well, it's one of the cases, so let's see what happens. So as you see, that after a while we have all this turbulence structure actually appears inside the accretion disk. And there's something actually interesting about this simulation is that despite of the turbulence, we still have like a thin structure on the equator. So dense matter is still on the equator. And we have this actually like what I call it like inner torus or mini torus. It's being formed here that is geometrically thicker compared to the rest part of the disk. And the magnetic fields are looping at this region. It's basically forming some sort of like plasmoid structure. And this is almost what happens to like all the cases except this one. So basically the cases with lower inclination angle for the magnetic field shows the same kind of structure. This is like the magnetic field at the final snapshot. So we have like this still thin structure to the end, and we have like single or even multiple plasmoid structure being formed. And this case belongs to the case that we have a higher inclination parameter, and as we see that this disk is actually expanding vertically with like magnetic field lines being like reshaped as like vertical, and you also have like not much fluid close to the black hole. This is the sign of like having a magnetically arrested disk, or what they call it MAC state. All right, so we claim that we want to actually measure alpha from this simulation, so we should do some MRI analysis because MRI is responsible for creating this alpha viscosity. So as a first step, so we can compare this wavelengths of the fastest growing one with the scale height of the disk. And we know that if lambda MRI is actually greater than h, it means that the MRI is suppressed and it's not effective anymore. So that's what's happening at the inner region of all these cases. That this is exactly actually the place we have this plasmoid structure being formed. So we see that MRI is not really effective here in these regions. From the surface density, also we can see that there is really distinguishable, radii that is actually this thicker part is actually separated from the rest of the disk. And also, so the other important scenario is maybe we don't have MRI always effective in our simulation, and that's happening when the magnetic field becomes too strong. That again, it's like it's actually making this turns to the matter state or magnetic arrested. So it's usually actually people measure this ratio of the magnetic flux to the mass flux at the horizon, and if it's actually big enough, we call it this MAC. And so that is what's happening for our higher inclination angle states. That you see the blue curve basically have this high ratio, and it's sort of actually showing episodic accretion behavior. So this case basically doesn't have much MRI. So so far we can say that there are possible scenarios that we don't have MRI, so not really effective alpha viscosity and torque from it. Okay, now let's move on and measure the alpha viscosity. So we use this relativistic approach by McKinney. And so we basically measure the Reynolds and Maxwell contribution from the stress energy tensor. So here in one of the cases, as we compare this Maxwell part, is the dominant part is has the contribution over 90%. And comparing the different basically different cases. We see that this average alpha can actually change a lot during time. So it can reach to like values up to 0.3, and also like it varies from like 0.3 to 0.1. And so far it's also the results showing that alpha viscosity cannot be constant, but it can also change with time. And the other analysis is here that we can actually measure the time average value for alpha, and again we see that in this radial profile that alpha can actually change it again a lot. You know, it's like at the inner part when MR is not active, we have very tiny values of alpha, and well, at larger radii we have basically alpha reaching to values like 0.1 or 0.2. So basically different parts of the disk has different kind of alpha viscosity. Okay, the next step would be estimation of the viscous torque. So the alpha measurement was directed from the simulations, but here now, because we don't have the secondary black hole, we need to use some sort of approximation for that. Again, we refer to the another one-dimensional model suggested by Shapiro. That's for the again, one-dimensional relativistic accretion disk based on Chapman-Smythe model. So this is how we estimate the viscous torque, and compared to the Newtonian part, it's almost the same, but it's got more complicated, terms which contains, the basically black hole spin and also like the coordinate values in the Voigt-Lindquist coordinates. And at the end, we compare this viscous torque with the gravitational wave torque, which is just estimated by this equation, because also gravitational wave also emission can just, that it shrinks, that the orbits move the binary getting closer. So we can do some comparison here. So this is the ratio of the viscous torque to the gravitational torque, and so here we see that again it's these are now it's representing basically the binary separation in a binary system, and so we see that binary separations, this ratio can reach to like values like 10 to the -2 or even higher. So it's suggesting that the viscous torque can be as big as like 1% of the gravitational wave torque, which should be detectable by future laser detections. Okay, now we can do some like very hand-waving estimations for the to estimate how much phase shift we can observe in the gravitational wave due to these environmental effects. Again, we kind of roughly estimate that for a binary system with like primary 10 to the 6 solar mass and the secondary 10 to the 3 solar mass. For the spiral phase, we kind of expect to have like 1 millihertz gravitational waves, and like doing these hand-wavy calculations, finally we concluded that we can have like about 10 radians of the phase shift for about 10, in about 10 to the 5 in spiral orbits, and 10 to the 5 in spiral orbits is about like maybe 2 or 3 years of observational time for LISA. Okay, so we did this analysis, but there are also other important things, but again, because we don't have the secondary black hole simulation, it's not possible to make a very strong statement here, but other papers actually suggest that the torque fluctuation can be also important. So in addition to the linear torques, actually we have the nonlinear effects and time-dependent effects, which can actually create additional phase shift in the gravitational waves. And so we have more stuff coming from the environment in the gravitational waves. So here we just actually monitor this ratio of the viscous torque to the average values. So this is comparing, this is actually change over time. That we are comparing, for instance, like two different radii, 50 and outwards 75. So we see that fluctuation is there, so definitely the torque is actually changing a lot by time. And even we have sometimes we have this like the viscous torque actually has a different sign, which is coming from actually the fact that in our measurements sometimes this viscosity becomes negative. And this is again coming from like the fact that we are applying a one-dimensional approach to a two-dimensional turbulence simulation. So, yes, now conclusion. So we basically found that the initial magnetic field configuration plays an important role to trigger and sustain the magnetorotational instability, or doing the opposite. And we also observed that the volume average alpha viscosity can vary between 0.1 to 2.3, which is higher than what the analytical model used. They usually use 10 to the minus 2. And the MRI is suppressed at the inner part of the disk, and the thick hot mini torus is formed. And we apply this one DGR hybrid approach to estimate the viscous torque, and we find that the viscous torque can be as big as like 1% of the gravitational wave torque. And so monitoring the viscous torque would also suggest that fluctuation can actually is there, and it can change the values of the torque by order of view. But this is all just the beginning, but for future studies, we basically need to add Warsaw. For sure, we need to do our GRMHD simulations in 3D, because like all this, MRI and also magnetic field evolution is really important to be in 3D. In 2D, we are limited by antidynamic theorem. For instance, we cannot have a very long simulations. And of course, we need to add the secondary black hole as a perturbator. So in that case, we can do a direct measurements of the torque. So basically, we can use a very like a straightforward, relativistic formalism for measuring torques. And it would be also interesting to have Fourier analysis of the torque fluctuations. And so when we have the secondary black hole, of course, we can study both disk-driven fluctuations and the perturbator-driven fluctuations. And so that's basically our future plan. At the end, I need to just remind ourselves that we are dealing with a very messy scenario. We have the binary system, we have the accretion disk, so matter is there, and there are also different scenarios that can happen, and also there are other mechanisms for the angular momentum transport. So you may have like the lead law or rotational resonance torques that can be responsible for the angular momentum transport, and there are also some relativistic effects such as the horizon flux that happens when the distorted horizon of the primary black hole couples with the tidal field of the secondary black hole, and again can actually make some angular momentum transport happen. And so it's really hard to distinguish really between all this physical process. And on the other hand, we know that if the gravitational waveforms is the heat from what we have in the vacuum, there's also possibility to actually explore the modified gravity of theories, but again, we need to just consider all these environmental effects and other effects that can actually create this space within the gravitational waves. So there is a lot to do. Thank you.
Are there any questions for the speaker? 2D and 3D is very different. So the models are having different configurations pretty polar, right?
The initial grid?
Yeah.
Yes, yes.
You don't have to write all things.
No, that's
Because they convert into. Could you have also variable fields?
for initial configuration. That is, I think it will, well, in the evolution, finally we will have, because the magnetic field will winding front and back or forth, so the toroidal components will appear after that, but.
Yeah, but in 2D, if I remember correctly, those kind of grow, which MRI does not affect.
That's right, that's right. So, yes, that's another reason we really need to have like 3D
Yeah,
simulation.
that was my question. So maybe 3D numbers you get for alpha will be different.
Right, yeah, I agree.
Because of that, besides because it's
Yes, definitely. Yes.
Okay, thank you very much. So let's take this because